All right. So just to sort of preface this a little bit, this is something that is very much a work in progress. So I'm excited to show it, but it is far from the final product. But with that said, let's get into it. So this is going to be my work looking at how rifting works on Venus, and then more broadly, sort of looking at how regional tectonics operates on a planet with a really high surface temperature, with heavy influence from volcanism. And this is work that I'm doing with Luc Lavier and Doug Hemingway. So we're going to start off with sort of a primer on what Venus is like and why it's so important to planetary science. At first blush, when you look at the bulk physical properties and chemical properties, Venus should be a lot like Earth. It's only slightly smaller than Earth. It's got a very similar mass, very similar gravity. It's got a similar-ish distance to the sun, where it has where it has an orbital period of 224 days. But then the differences start to kick in that it has a solar day of 116 days and a sidereal day relative to the background stars of 243. And if you notice the negative numbers on that slide, it's negative because Venus goes backwards from the rest of the solar system. So already early on, baked into Venus's history, there's something weird happening, where something happened early on that caused it to become very different from the Earth. And this carries forward into some other key observations. In addition to the retrograde rotation, it has no internally produced magnetic field. Is there a way that I can move that out of the way?
Do
do that. That one.
There.
Yeah, then we just move that up into the corner. Yeah. Right. So yeah. So in addition to the retrograde thing, retrograde motion, it also has no internally produced magnetic field. And that, because of the similarities to Earth, that's kind of odd because Earth is a very powerful magnetic field. The only magnetic field that Venus has is an induced magnetic field from the solar wind interacting with the upper layers of the atmosphere. It's also a highly volcanic and tectonized planet, with a mean age of the surface based on crater counting of anywhere between 500 million and a full billion years old on average. Because there's only, I think, 900 craters, give or take, across the whole planet. So it's a pretty small sample size, and it's very difficult to interpret. It also has no apparent evidence of plate tectonics, which is another key difference. So and I'll get into that more, but I think it's important to note that we don't really have a whole lot of constraints for Venus's geodynamics and its geology. While it has had a bunch of missions go to it, all of the data as far as the geology and geophysics is concerned mostly comes from these 6 missions. Up here you have Pioneer Venus, which was a fleet essentially of probes that descended through the atmosphere. But en route and during the descent, they took radar images. And following that up, you had the Magellan probe, which was essentially just a synthetic aperture radar with an altimeter mode and a radiometry mode that mapped, I think, I want to say like 87 to 93% of the surface. And that's all from orbit. The only in situ measurements of the surface come from the Vega 2 spacecraft and from Venera 13 and Venera 14 out of the Soviet Union. So that's really important to keep in mind when we're talking about what the actual rocks are on the surface. Because essentially we have 3 data points. These are the only 6 images ever taken from the surface of Venus. And then these are the 3 data points we have for composition. And then from these chemical composition, we have backed out a presumed mineralogy that is essentially Morb-like, but that is it for the whole planet. So let's just point out that there's a lot of unconstrained mysteries. On a more global scale, we're looking at a planet that is very different from Earth. So here in the atmospherically, it's very distinct. At the surface, the pressure is 93 atmospheres. where CO2 isn't even a gas at that point. It's actually a supercritical fluid. So it behaves and reacts very differently from what we would expect. Temperature is also very high. It's 470 degrees Celsius. So to a certain extent, the standing on Venus's surface would be very much like standing at the bottom of an ocean, to a certain degree. It's also worth noting that the global geology is very mysterious. It's kind of dominated by these low volcanic plains. And then you have these high plateau regions like Ishtar Terra up here. And then Aphrodite Terra here, which are these high plateaus, but they're both very distinct from each other. This is very tectonized and divvied up. But this is also, has this Himalayan scale mountain belt that looks like a collision between this area, Lakshmi Planum, and this area, Fort Tesseract. So geologically, there's something dynamic happening here. And furthering the interpretation of like dynamic geology on the surface, this is a slide that I pulled from the European Space Agency, kind of showing the as of 2022 evidence for active volcanism on the surface. You have variations in sulfur dioxide abundance as a function of time that is most easily explained by large volcanic eruptions. You have areas of anomalous microwave emissivity, which implies a very young, unweathered surface at the tops of some of these volcanic edifices. And then you also have these transient hotspots picked up in infrared along these rift valleys, implying that you have recently had eruptions. Now, this was all sort of circumstantial up until earlier this year, where Herrick and Hensley went back and they looked at some old Magellan radar images and were looking for differences between one cycle of images and the other cycle of images. And what they found was evidence of a volcanic eruption taken in the 8 months between these images were taken. The really key thing is that this caldera down here has enlarged and completely changed its shape. And it's changed its shape in a way that kind of can't be reproduced from just looking at it from a different angle in radar, because you're going from essentially just a circular feature to this kidney-shaped feature. They also think that they might have seen some, possible new flows, but that is uncertain. And then for comparison, right, here's the unchanged vent, which hasn't changed its shape at all. And if it was a function of look geometry, that should have also have changed. So this is pretty, this is the best evidence so far that there is, in fact, active volcanism occurring on Venus. So Venus is this very dynamic world, possibly with Earth-like levels of activity into the present day. In addition to that, it's also got these other Earth-like features. These are the Maxwell Montes, which are that Himalayan scale mountain range I talked about earlier. There's also have widespread rifting across the planet, and you also have these anomalous terrains called tessera. Tessera are a morphological definition to basically describing a region of radar bright rock that is crisscrossed with many different episodes of tectonic activity, and they are also embayed by the surrounding volcanic plains. They are generally considered to be the oldest features on Venus's surface. And many people have pointed out the similarity between them and what cratons look like on Earth, which is a very interesting hint that some of the early histories of the two planets might have been somewhat similar. We also have, like I mentioned, widespread rifting. And this is what I really want to focus on for the whole rest of the talk, is how rifting occurs and how it evolves and what role does it play in the overall geodynamic story of Venus. Speaking of the geological story of Venus, this is about the best stratigraphy anyone has got so far, where you have, the old tesserae early on with this very highly tectonized environment. And then you have these subsequent units that are all very volcanic. This is the flooding of the lowland plains with lavas. There isn't that much tectonism occurring outside of like minor extension and things like that. And then later on, you get some more robust, in the more recent history, you get this robust tectonic and volcanic activity that continues possibly into the present day. But as you can see, like, this is all very uncertain. This is all relative time. This is based on stratigraphy done from orbit. So this is all very uncertain. And it also leaves open the question of, okay, what is Venus's geodynamic regime? What is it doing that it changes so often, or it can be, it's so difficult to interpret? And recently that has focused around these three different end members for how Venus should behave. The oldest one was put forward in the 90s. It's called the stagnant lid model. Stagnant lid implies that during convection, you don't have any exchange between the surface and the interior. Heat is lost conductively through the lithosphere, and the lithosphere never, is recycled back into the mantle, at least not completely recycled back into the mantle, like it is with plate tectonics. Then, in order to explain some of the activity and some of the tectonism, because stagnant lid implies it's kind of stagnant behavior, there's not a whole lot of horizontal motion. You might have gradual resurfacing through volcanism, but how do you explain this sustained topography and things like that? People have invoked this idea of the episodic lid, where you have a stagnant lid that eventually weakens because it's not efficiently losing heat. And then as soon as you create a break, the entire lithosphere sort of catastrophically subducts over the course of a few tens of millions of years down into the mantle. You recreate a new lithosphere, and then that thickens up, and then you run through the whole process again. This has been called into question recently because of some difficulties in explaining some of the observed geology and current activity. Like, if it's quiet in between catastrophic overturns, then why are we seeing such modern activity? And then this leads to the third and most recent one that was put forward only a few years ago with the unfortunate name Plutonic Squishy Lid. Well, I'd say unfortunate. It's a little goofy, but it is pretty accurate. The idea is that you have a surface that is dominated by intrusive activity. So lots of plutonism, magmatism, that is driving resurfacing, but you still have limited amounts of horizontal motion because the entire lithosphere is very weak, very squishy. And so what you can have convective overturn of the lithosphere, it's happening very, very locally because the lithosphere isn't strong enough to form large plates. So that's been a more recent hypothesis. So in light of that, let's move back to the one planet we know has plate tectonics and look at the Earth. And the Earth sort of has a couple of big diagnostic features that are important for identifying plate tectonics. One is the presence of the mid-ocean ridge, right? This global system that is responsible for the resurfacing of most of the Earth. It's very, very identifiable because it's essentially one single system. And in addition to that, you have the hypsometry of the Earth. So this is altitude along this axis. This is the percent of the surface area. You can think of it like a histogram of elevations. And you get this bimodal distribution that is indicative of a crust of a lithosphere with two different compositions, continental crust and an oceanic crust. If you go to Venus, Venus doesn't have that. It has a unimodal distribution, but it's not a normal distribution. So there might be while to first order it's all the same composition, you might have smaller regions that are maybe, more felsic than gabbroic. But then also kind of zooming out, looking at a map of Venus, while you don't have a global mid-ocean ridge, you do have a global rift system or rift systems, because you have this very strange pattern of interconnected rifts. On Venus, they're called chasmata, plural, singular chasma. But these chasmata intersect. They tend to link different volcanic centers across the planet. And all of these volcanic centers are places where people have, proposed activity. So this active volcanism I was talking about earlier is happening in Mont Mons here in Atla Regio. There's also been proposed activity up in Beta Regio as well. So this whole region right here is of key interest. It's called the BAT, or the BAT, for Beta Atla Famous, which is So this is a global rift system, but it's very distinct for the mid-ocean ridge. And that's interesting because if the mid-ocean ridge is the key to understanding plate tectonics, now understanding this global extensional system is maybe the key to understanding Venus's own geodynamics. So the questions that I really want to ask is, an analogy to the mid-ocean ridge system on Earth, are the chasmata places where you are forming new Venusian crust? And if that is in fact the case, then we should be able to show that geodynamic and geophysical models that incorporate magmatic accretion in a Venus-like environment should be consistent with the structure and topography of Venus's own rifts. So this is kind of leading into how I set up some of the models. On Earth, the driving force for plate tectonics is slab pull, which we don't seem to have on Venus. There might be regions of local subduction, but there is no global subduction system. So right out, slab pull is probably not an important driver for most of the surface of Venus. But what that leaves you with is you're left with ridge push or plume push, possibly also with mantle drag, as the convective pulling at the keels of some of these plateaus. So already the tectonic rates are going to be low, possibly at least an order of magnitude lower than what you get on Earth. And in fact, they could be as low as 2 orders of magnitude less than the kind of tectonic rates you get on Earth based on crater deformation. Basically, seeing how craters deviate from circular in order to get an idea of how much strain has occurred. The other key important part of the model is looking at the process of eclogitization. When gabbroic rocks are at sufficient pressure and temperature conditions, then they undergo a phase change from basalt into eclogite, where they're a lot denser and they're also a lot weaker. And on Venus, this is actually really key because on Earth, looking at this map, this phase diagram looks scary, but I promise you it's actually really simple. Just look at the green stuff versus the white stuff. Ignore every other line. It's just this curve right here, where it's basalt on this side, eclogite on this side. On Earth, the geotherm does something like that and intersects relatively deep. On Venus, because of the higher surface temperature, the geotherm is going to be sitting somewhere around here, and you're going to intersect that area of the phase diagram much more shallowly. And as a result, you're going to create more eclogite, more shallow. So it's going to play a very important role, not just at deep inside slabs like it does on Earth, but also could be able to play an important role inside the lithosphere. So this is the parameter space that we're exploring. I talked about extension rates. We're going to go from essentially the low end of Earth-like all the way to 2 orders of magnitude down to the much more conservative estimate of 0.01 centimeter per year. We're also going to be varying accretion rate at the same time. The reason for that is because we're prescribing an accretion rate where you have a dike that forms, it creates new crust, and we're going to create that new crust at a certain rate. And that rate can be in equilibrium with the extension rate in order to create something that looks like seafloor spreading. But we also want to be able to test examples of hyperextension, where maybe melt is suppressed because you have a depleted mantle, or it's unusually cold, or something else along those lines. Or the opposite case, where you have a lot of excess melt, maybe because you have a plume or some other kind of hotspot. And we're also testing this at 2 different heat flows, 50 milliwatt per meter squared and 80 milliwatt per meter squared. And what that really means is that this is thick lithosphere, that's thin lithosphere. So we also want to validate these models, not just run them in a vacuum. So we're picking certain regions on the surface of Venus that are relatively well geologically mapped, that we have data for. And one of these places is Hecate Chasma. It's part of that BAT region, so that active volcanism is down here. off screen, but this is a rift that connects. So these lines up here are the escarpments along the rift that continue around to go here. This whole area is interrupted by different kinds of volcanic features. Like there's a shield volcano up here. There's also what we call Taranga corona. A corona on Venus is a circular tectonic magmatic feature. So they're defined by concentric faults with a volcanic center in the middle. They're usually somewhat elevated with troughs around the outside. They are unique to Earth with an asterisk because there have been some identified possible coronas in the Archean rock record on Earth. There's some circumferential dike swarms in Africa, like at the Victoria Lakes region, that might be what a corona looks like if you shaved off the top. So keep that in mind. So unique to Venus with an asterisk. So that's what we're going to benchmark these models against. So we're going to start off with a very simple C4 spreading model. This is case number 8 with a millimeter per year accretion, millimeter per year extension with a low heat flow, so a relatively thick lithosphere. This up here, this is the gabbroic crust, the basalt. This down here is the mantle lithosphere. The asthenosphere is down here in the dark green. You're going to see a few new colors pop up. This dark gray that's going to pop up in the middle, that is also basalt, but it's the new basalt that's being formed at the dike. And you're also going to see, not in this model, but in the future model, you're going to see black, which is the eclogite forming and then delaminating down into the mantle. You're also going to see yellow, and that yellow is where you have this high temperature shear zone forming, where you have damage rheology and you get a very weakened mantle along which you can create detachment faults and shear zones. So, and then this white over the top, that is strain rate. So areas where it's white, you're going to have a very high strain rate. But I'm going to fast forward this because it's kind of long. But basically what we create is something that is a pretty straightforward looking mid-ocean ridge analog. You don't quite have a ridge, but you are creating new crust. And then, through pure circumstance, there's a spooky ghost face that just shows up, because of the way that you have like this small convection happening in the mantle. Has nothing to do with anything. I just think it looks weird. So that's case number 8. And here we're going to show the same sort of thing where it's also C4 spreading, but we're going to have it at a higher rate. So instead of slow spreading, it's going to be fast spreading at centimeter per year. Now, this is where the eclogization is foreshadowed a little bit, because you're going to see some of this stuff drop off into the mantle. And for really high accretion rates, that's going to become really key. But for now, we are creating a relatively thin layer of new Venusian crust with some slight delamination occurring. And in topographic profile, this is what that looks like. For the first slow case, you get a relatively deep but narrow rift. And then for the faster case, you end up with a somewhat broad, wide rift with a lot of faults in the middle. So there's a lot more structural complexity occurring. You also have this little bump in the middle, which is the actual ridge itself. That's the hot dike that is isostatically compensated. It's up high. So this is what that looks like when you compare back to Hecate Chasma. This is cross-section 18 down here. That's cross-section 8 up here. This is what that looks like when you compare to the real data, which is in orange. So certain parts of Hecate Chasma are consistent with either slow spreading or fast spreading. Now we're going to move on to a centimeter per year accretion, which is much larger than the 1 millimeter per year extension. And it's going to look very different. As you overthicken the crust, you're going to form these large eclogite roots. And eventually what happens is the eclogite just weakens and then drops off. The white is the high strain rate. But it's going to weaken and drop off into the mantle. And you're going to create a very different structure where you have these troughs along the outside. You got this volcanic center in the middle. You've got all this structural complexity in between. And this is starting to sound a little bit familiar for those who studied Venus. Here's what that looks like in profile. Trough, volcano, and then once the delamination occurs, you get a topographic inversion. You still have the troughs on the outside, but it's kind of overprinted by this, sinusoidal pattern. And this might sound really familiar, people who study Venus, because this is starting to sound a lot like the corona. This is Taranga Corona in the middle of Hecate Chasma. And here I'm kind of just running through and looping through the model. And you can see that central peak matches, the trough on the outside matches, the scale of deformation, that wavelength of deformation is also a relatively close match. But what we're missing is that plateau. We're getting a full topographic inversion. What I think is happening is that because we prescribe an accretion rate, we're not generating any melt natively to the model, really the crust should be more buoyant than what the model represents. With all the small scale convection occurring as the delamination drops off, you should have migrating melt centers. And these migrating melt centers are going to heat up and support higher topography. You might also have, maybe, you can always invoke a plume if you want. But, that's the idea that the coronae might be consistent with this overthickening of the crust and delamination, which has been proposed before for different other coronae on the surface, such as the grandmother of all corona, the Artemis corona. This is 2,000 kilometers across. It is absolutely massive. It's the largest corona on Venus, to the point where I even hesitate calling it a corona. It might actually be its own thing. And that own thing that it might in fact be is a subduction trench here with back arc extension, as this whole entire system is rolling back. Because it is radially asymmetric. There is no trench back here. So it does look to a certain extent like this is all just rolled backwards like that. And it kind of makes sense, right? So this rift in here is called Breda Martis Chasma. It is linear, and then it jumps along a transform margin, and then it continues to be linear. So it looks a lot like a seafloor spreading until you get to the south where things get a little bit weird. Where you get this big arcuate curve in the rift. And then you have, all this interesting shield volcanism. And then you also have a random impact crater in the middle of that. But there's some sort of complexity happening to the south that doesn't match what's happening in the northern part. And so I wanted to test and see whether or not Breda Martis Chasma, like some of the other chasmata on Venus, could be consistent with seafloor spreading. Here is K15. It's 1 centimeter per year accretion rate, 1 centimeter per year extension. So it's another seafloor spreading analog at a thicker lithosphere. And this is interesting. I'm going to pause it right here. Oh, no, that did not work. I'm going to pause it right here. So you can kind of see that there's some asymmetry developing where the dike is here, but the Hofgraben has formed off to the right side of the graben. This is something that we see a lot on Earth. Essentially, it's very hard to create actual symmetry in a rift. Things tend towards asymmetric because it's more efficient to deform through simple shear than to deform like through a fully symmetrical system. And that is what is happening here. So you develop into an asymmetric rift system, if it will let me play the dang thing. Thank you. So you develop into this asymmetric rift system where on the right side it is thinner and on the other side it is thicker. Delamination also plays an important role. Unfortunately, it's kind of getting overprinted by the strain rate signal. It's something I will fix in future animations. But that is essentially just that is eclogite delaminating off and falling in down into the mantle. So you can see there's this inherent asymmetry. I also wanted to test a case that was very melt rich. So we've had a very thin lithosphere. So here you can see again, delamination. You also create this peak in the middle, which you don't see in the other cases. And I wanted to test these and see what they looked like compared to the actual topography of Breda-Martis chasma. And see whether it matches the back arc, asymmetric back arc extension or some sort of like magmatic peak forming. And what you end up with is again, this is qualitative because I'm comparing squiggly lines to squiggly lines, but you do get an actually pretty good match between this northern part of Breda-Martis chasma through this asymmetric back arc extension. That's a pretty good match compared to the purely volcanic case where you have really low extension, high accretion, where you get the central peak, but the rest of it doesn't fit at all. Not really. It's too symmetrical. It doesn't have the right depth. It doesn't have the right slope where it's steeper on this side and more shallow on this side. So the idea here is that Artemis chasma is in fact possibly, consistent with back arc extension. You can also, moving further south, this is that same case just further along in its evolution, and it does match the middle part of Breda-Martis as well. But moving to the southern part of Breda-Martis, where this rift curves around, right? So if this whole thing is rolling back this way, then the strain rates here should be pretty low. So if we use the slow spreading case, we actually get an okay fit, at least in terms of width, not so much in terms of depth, but it is somewhat suggestive. Moving on to another location, this is Diana chasma. This is actually related to Artemis. So this is that trough that is hypothesized to be a subduction zone. Here's Breda-Martis once again. It's another one of these rifts where you have a bunch of coronae interrupting the path of the chasmata. The other important thing here is that it's also very fragmented. So you can have a block here, smaller blocks here, blocks here, blocks here. It's a very fragmented region where it seems to be like, platelets or microplates, very much in line with the plutonic squishy lid idea. So here's case 3. This is, because of the high extension rates, I wanted to test whether or not hyperextension could be applied here. And it turns out that, yeah, maybe. So this is a case where you have the melt is suppressed. So when you're extending, you're hyperextending. You're exhuming the mantle up to the surface, and what's being exposed at the surface, if it's not covered by lava flows, is going to be things like mylonites and other things you would find in a high temperature shear zone. And also in the topographic profile, this has a very distinctive appearance where you have this, steep-sided bowl where essentially you're just pulling, the mantle up to the surface. So matching that, we actually do get a pretty good match with that. So this here is where you have, compared to like case 15, for instance, this asymmetric spreading case doesn't quite fit. Not really. It's too sloped here. This peak isn't quite big enough. It doesn't have the right structure. It's just overall not a great fit. But if you look at case 3, if you look at case 3, you have this deep bowl with steep sides that can somewhat match the observed rift morphology. And that this over here is probably just a second rift splayed. It's specifically like this thing right here. So this might be another instance where you have rifting is consistent with the idea of hyperextension. Kind of zooming back out a little bit. Sorry, I've got a migraine. Zooming back out a bit, here you have, here's the whole parameter space color-coded to the kinds of morphologies that we get in the models. So the blue is where you get the light blue is where you get hyperextension, which makes sense if you're getting it in this high extension area with low accretion. This dark blue, purple, and green, those are the different seafloor spreading analogs, where you have sometimes with shear zones, sometimes with minor delamination along the base. And those are going to form this more or less like sort of like middle ground diagonal line right about, here or here. And then the yellow is where you're going to get that really intense over thickening and delamination where you're dropping lots of material down into the mantle. So zooming back out a little bit, what does this tell us about this overall rift system? Well, first of all, you can see that they tend to be in association with these volcanic centers. And then you have this rollback trench here with this rift in the middle. And so, one of the questions is brought up, it's like, okay, well, if you're creating all this new crust along these areas, where is everything subducting down? If it's, what I think is happening is that it's not subducting down elsewhere. I think what's happening is you're having this crust of recycling and extension happening superimposed on top of each other. So you have this global rift system that's consistent with magmatic accretion. The coronae might be places where you have excess melt, possibly due to a plume or some other like small scale convection and local instabilities. Eclogenization and delamination are going to be really important processes for crustal recycling on Venus, but they're happening exclusively on a regional scale, which is fun because this is starting to sound a little bit like Plutonic squishy lid. And that's in and of itself is fascinating. Future work is going to be improving the treatment of melt production and heat transport. We're also going to look at the gravity and see what kind of predictions we can make ahead of future missions to Venus, because the gravity profile from these could be it could be a diagnostic that you could actually, go and take that measurement and determine what's happening in the subsurface. So that would be really important. And finally, we're going to do some more quantitative analysis. Right now, we're still doing like classical geophysics of squiggly line to squiggly line comparison. But in the future, we're, going to be characterizing all of these different rifts, figuring out which ones match the best to which kind of model, and then mapping that out across the global rift system in order to really understand the dynamics of what is happening on Venus geodynamically. One last note before I finish. All right, would you move, please? No. See, this is the first time I put an animation in any of my slides, and it's being weird when I want to move backwards and forwards. On another note, I would like to add that there's never been a better time to get into Venus science. There hasn't been a mission in 30 years that NASA has done. However, 3 new missions have been greenlit. Veritas through NASA, Da Vinci through NASA, and Envision, which is a European Space Agency project, but some of the instruments are being built at JPL and being managed out of the University of Arizona. Sorry. So 10 years from now, we're going to have a wealth of new data to answer a lot of these questions. So people are going back and they're re-looking at the Magellan data. They're looking back at some of the, data that come from some of the older missions, like, people are even going back to the Venera and Pioneer missions. There's never been a better time to get involved in Venus. So, please join us. And that's the end of this talk. I hope you enjoyed some of the preliminary stuff that I've been working on, and I hope you improve it soon.
Questions?
Oh, it was it was the same time. Ed.
Okay, so you're just like setting different extension rates.
Yeah, we're prescribing an extension rate. We're prescribing an accretion rate.
So you mentioned a little bit about what you thought driving that, but you thought in more detail than just it could be a boom or
yeah, I have thought about that, but it's not something I've modeled.
Okay.
My thoughts is I think what the driving forces are is probably plume related. like not necessarily the plume like coming up and rifting apart, actively rifting things apart. I mean, like the plumes are going to build these big volcanic edifices. They're going to collapse gravitationally. And then you're going to have delamination as they overthicken. And I think that small scale convection is what's probably driving some of this stuff. That's would be my guess. Because like if you look at, actually, this is a really good example, right? Like, you know, the rifts seem to link these big, you know, like volcanic centers. And like this is nothing but like a pile of different shield volcanoes, kind of like Elysium on Mars or a smaller version of Tharsis. But it's the rifts link these things. So I think there might be some gravitational collapse driving at least this system in the BAT region. And over here, I'm not quite as sure. There seems to be some like trench rollback that might be driving at least Brita Martis, but like it's all in association with the southern edge of this Aphrodite Terra plateau. So maybe there's something happening at the edge of that plateau dynamically that might be driving it, but I'm not sure what that would be.
Do you have any plans to actually more quantitatively?
Yeah.
Because I was looking at some of them and I was like,
yeah,
I'm not convinced.
No, I agree. I wouldn't believe me either. This is like I said, this is very much work in progress. No, we do have plans to quantitatively look at this. We're thinking about using admittance and other kinds of power spectra methods in order to break down what kinds of signals are going to be most important, whether that matches up with the real data. The other thing is we're going to do some characterization, looking at the widths of rifts, the depths of rifts, whether they're asymmetric or not, the slope of the rift flanks, the kinds of internal structure you might find in that kind of thing, and basically pull up like a scorecard of, you know, okay, what looks best and can we match it? It's just that's a lot of work. So that's only just started.
Have you considered that maybe you're going to need to like smooth or filter the data because your full resolution is not the same as the resolution?
So those are the smooth versions.
Okay. So it's still a kind of
there's still an inherent I smoothed it to the point where the noise, where what I think is the noise has disappeared, but there's still a lot of like structural complexity that comes to the fact that, like, you know, there's going to be lithospheric heterogeneities and pre-existing structures, and rifts are going to intersect in three-dimensional ways. So one of the ways that we're thinking about treating with that is looking along a single rift and then looking at transects across it and sort of, you know, not adding up, but essentially like averaging across. As a way to do that. But we'd have to pick those rifts carefully. Otherwise, you might get noise from like other intersecting features.
Yeah.
This might be a silly question, but why do you think you see like your different models apply in like different locations along the same rift? Like what's the spatial extent?
It probably has. I don't know, because it's work that I need to further explore. One possibility, if those matches are true, which is a big if those matches are true, it might be that, you know, you could have the rift being opening at one end and the rift tip might be somewhere else. You know, you might have like, it might be a certain degree of rotation. You might also have, you know, issues of like, for the love of, okay. This is a good example here. What? Okay. Yeah, this is a good example here. Like along the same rift, the thing is that this is a separate block. And so is this down here, right? So these blocks might be moving at different rates from each other, right? Because there is, you know, some sort of rift along this edge here, and that this is possibly a corona, and yeah. So there's going to be some kind of complexity that is changing the regime along rift.
Can you explain a little bit more of this, like, what was it, like back arc?
Yeah.
I don't know.
Yeah.
Play with that term. Like the
Sure.
geometry of what's happening.
Okay, so you want me to explain the geometry or like what back arc extension is?
How about both?
Okay, cool. Yeah. So the idea is that you have whatever this plate is subducting underneath this area here. So this would be the subduction trench. But as that like plate, let's see if I get the orientation right? As it's sinking, it's going to roll back. And as it rolls back, it's going to suck that overriding plate out towards it.
Okay.
And that is going to create extension in the middle. This is something you see in Asia, like, the Philippine Sea Plate. You also see it in Indonesia. You see it in Kamchatka. You see it all over. In the Mediterranean, you see this kind of thing as well.
Okay, thank you.
Yeah, so that's the idea, is that essentially like this might be a place where you have, because you have this regional subduction, you might have abnormally high strain rates compared to the rest of the planet. And that might be why you're getting this, extension in the middle.
So your accretion rates, is that kind of like melting?
No, it's not melt driven. We literally just say like, okay, this row of elements is going to be a dike. So we're going to add basalt in the middle, a certain amount each time step.
Okay, so what sort of controls that?
How do you get them? Nick controls it.
I control it. It's the knob that I turn.
Yeah. What does it mean though?
Yeah.
If you have like a high rate and a low rate, how does that happen?
Okay, so if you have a low rate, that might be because you have like a depleted mantle, so you're not melting very efficiently. If you have a high rate, that might be because maybe you have a plume or some other hot spot impinging on the base of the lithosphere. That could change the melt rate relative to the extension rate.
And when you were showing your plots for the corona,
yeah,
you had a low rate for those plots, right?
It was a high accretion rate for those, okay. And it was a low extension rate because for those structures, like the relative rate is most important. Yeah. Could I? Okay. I'm gonna. Da Vinci and Envision are on schedule, and they're on schedule to launch. Veritas got delayed, and it's.
Da Vinci is the more atmospheric one, right? Or is that?
It is more atmospheric. It's a probe that's going to be dropped, but it is, once it passes the cloud layer, it is going to take very high resolution images, and it's going to land on top of one of those tessera. So it's really important for the geology as well. It's sort of split both ways. Da Vinci in it because they aimed it at it.
But isn't it like winds?
Well, actually, the winds are fairly well characterized. The atmosphere is really, really thick, which means that it's really like heat is very evenly distributed across the planet. So wind speeds are actually like really low. And people have dropped probes into Venus's atmosphere before. So they generally go where they're supposed to.
Okay.
So there is a landing ellipse for Veritas. I think it's also guided because they have parachutes, and I think they have rockets as well.
Okay, cool.
I gotta check.
Yeah.
So Da Vinci is really cool. It's very cool. But yeah, Veritas, because of budget problems related to Mars sample return and the delay of some other missions. This is gonna be recorded. This is gonna be on YouTube, right? Like this is all recorded. This is recorded. You know this, right?
Everyone knows I'm a Mars hater.
Okay. All right. I was going to say like, I'll talk to you after the recording button is off. But no, so basically because of Mars sample return and this delay, Psyche delay and some other stuff, 3 minutes. Because of all that stuff, there have been basically, in order to preserve the budget, NASA has delayed certain missions, and Veritas got hit especially hard. So its budget is 0 for the next year. Which obviously poses problems for like maintaining relationships to other institutions in Europe. And it also means it's going to overlap in time with Envision, which is a problem. So right now, the launch date for that's in negotiation. Veritas team hopes for a launch in 2029. NASA plans for a launch in 2031, but it is in fact happening.
Okay.
Yeah.
Okay. Silly NASA.
Yes.
Silly Mars.
Budgeting is hard.
I have a question.
Yeah.
I know you talked about the coronae,
Mhm.
but are they all associated with this, assumed to be associated with this subduction, or is it just
No? A good many of the larger ones are Taranga, Quetzalcoatl, Artemis, and some of the other, like Atahensik and some of the other big ones. Sure. There's some medium-sized to smaller ones that are not. Corona just really describes any sort of like strange circular structure that is assumed to be volcanic and tectonic. So there's very small corona that they sort of have like a profile that looks something like this, right? And they just have like rings of faults, but they're maybe only like a few, like 50 to 100 kilometers across at most. Yeah. So like there seems to be coronae aren't necessarily one thing. They might be many different things.
Thank you.
I didn't see any.
I didn't see any either. Okay. Thank you, Nick. Thank you, everybody, for coming.
Yeah.